Now let's go ahead and finally solve an example. I'm going to call that step 5 because it's going to put together many things that we have discussed in the previous slides. Okay. Now normally I would let you solve this and so that you practice with the ideas and methods that we have discussed in class. So I would actually presently as well recommend that you experiment with those ideas by attempting to solve it first yourselves. But let me describe first the problem. So what we have is, first of all, something like a plate. So I'm going to cook up this problem, right? It's not necessarily something that's very physical, but it will allow us to experiment with the ideas. So we have a plate, and that plate is connected to a surface. Okay, so that's a fixed surface. And underneath the plate, let's say there is a rod that eventually has a similar length, and then there is this other surface that I am drawing in dashed lines. It's a, say, I'm not indicating explicitly, but both of these are connected to this surface. Both surfaces are rigid. This one is fixed. Eventually I will be able to displace the other surface. Okay, so that's that one. Okay, good. So that's the problem we are looking at. Okay. Let me write down the dimensions. So first of all, this is the, let's call this h of 1 centimeter, and this is going to be the length, if you like, the initial length, 4 centimeters. And then there is the thickness of this plate, 2.5 millimeters, and there is the diameter of the rod, which is 5 millimeters. And what we are going to do is we are going to load this plate through a force. So this rigid plate is going to be displaced under the action of a force which is equal to 80 newtons. Okay. And the question is, find the change in the length. Okay. And in doing so, we are going to make use of the following material models in the nonlinear elastic regime of deformations. Let's call this 1 and let us call this 2 in relation to the numbering that we use for Fung and neo-hook material. This is going to be, let's say, skin. Say it's human skin. And this is going to be some hydrogel material. Hydrogel is a soft, very soft artificial material that we are going to eventually employ by making use of, or model by making use of, the neo-hook material. Okay, so this is used in tissue engineering. So here I also used a tissue eventually as a representative tissue. So the human skin is going to be the Fung material, associated with a Young's modulus 1, which is 1 MPa, and remember there is a free parameter alpha, which I'm going to pick to be alpha equals 0.5. And then in the hydrogel, we have a neo-hook material model with a corresponding Young's modulus of 5 MPa. Notice that the moduli are extremely small because we're dealing with here highly deformable materials. Okay, so that's what I'd like to do. I have the force and I'd like to find the displacement. So eventually I'll know what the stress is in some sense, and I'm trying to find this stretch, and therefore we need some nonlinear equation solution capability, right? And that's why I introduced the bisection method in the earlier slide. Let me go ahead and quickly evaluate the areas associated with these these biological structures. First of all, we have the first area, which is thickness times h, which is 25 millimeters squared. And then there is A2, which is pi over 4, 5 millimeters squared. That's the cross-sectional area of the cylindrical rod. That's 19.63 millimeters squared. So the areas are almost the same. They don't have to be, but they are the same, and therefore the moduli are not that different. So they will make significant contributions, both of them, to the corresponding force. I need to capture both of them accurately. So the net force is the area in the first multiplying the stress in the first plus A2 sigma 2. Okay? And now we're going to use our nonlinear elasticity model. So we know what A1 is. So we multiply with E1 divided by alpha. So now I'm writing the form of the stress from the found material, followed by A2 multiplying the form of the stress for the neo-hook material. And that's supposed to be equal to the force, right? Now, the force is equal to 80 newtons. The area is 25. The first one is 25 millimeters squared. This one is 1 MPa. Alpha is 0.5. A2 is equal to 19.63 millimeters squared. This one here is 5 MPa, and that's it. So that's equal to newtons. Now notice that millimeters squared 10 to the minus 6, 10 to the 6, they cancel each other, so I'll just retain the numbers and throw off the units. That's consistent with Newton on the right-hand side. And then I will put this 80 to the left-hand side and call that a equation F, which is now an equation of only the only remaining unknown is lambda. I'm trying to find lambda such that that minus 80 is equal to 0. And if you evaluate the numbers, you will find here that 25 times 1 over 0.5, 50, e to the power 0.5 lambda minus 1, plus this one eventually gives you approximately 41 lambda minus 1 minus lambda minus 130 is equal to 0. There's another eventually, notice, constant coming from there. That is minus 50, minus 80, minus 130. Okay, good. So now you can invoke our bisection idea. So we use bisection method. And here, notice we are using, again, let's highlight, it's a problem that's for nonlinear elasticity. I'll shortly make a comment on the type of accuracy or prediction you have when you neglect the fact that you are dealing with nonlinear elasticity here. So the bisection method starts off by, first of all, noticing that the force is positive, so I'm pulling, I expect a positive, of course, strain, therefore stretch is larger than 1. So first I go ahead and evaluate the value of F at 1, and we get a value of minus 131. Everything vanishes except that term. It's less than 0, as I expect. So I'm seeking a positive value, and let's plug in F equals 2. And when I plug in F equals 2, we get, in this case, you can evaluate that yourself, 25.9, which is greater than 0. And therefore, I know that my range is 1 to 2. And bisection predicts the midway as the first possible value. So that's 1.5, which is equal to minus 24.9. Now, 24.9 is in between. It's negative. That one's positive. So I'm supposed to go to the next range. The next range is the range. So this is less than 0. And so I'm supposed to go to the range 1.5 to 2. So the next thing I predict is F of 1.75, midway between 1.5 and 2. And if you plug in the value, you get 0.5. Now, notice we started from very large values. We are already down to 0.5. That's already a very, very small value. So we imagine that we might be very close. But to judge how close, let me give you as a reference value. The exact solution in this case would be not 1.75, which almost gives 0, but not quite. we're supposed to pick a value that's smaller than 1.75 because this is positive, right? So the exact value is not 1.75 but slightly actually smaller, 1.74507. But for our purposes, this is good enough now in relation to the exact value, which now I am providing to you so that we can judge that closeness ourselves automatically presently. In actual application, in numerics, there are ways of determining when to stop, so how far to keep bisecting. Presently, I just gave you the exact solution, and so you know that this is a good result. So now that this is the value of lambda, remember that lambda is the length divided by the initial length. So let us actually call this the initial length, Li. So the new length divided by the initial length is equal to lambda, which is 1.75, and therefore the new length is, since the old length is 4, the new length is 7 centimeters. In other words, the change in the length that I am seeking is equal to 3 centimeters. Okay? So if we go ahead and evaluate the strain, which is lambda, right? Lambda minus 1, or 3 over 4, is the same thing. It's 0.75, which is not a small strain. Okay. Now suppose, despite the fact that we expect such very large strains, let us comment on what would have happened if we had used linear elasticity. Now notice, and I emphasize that this is, it turns out, what we are supposed to use, not that. But how do I know that this is not a good idea to use? Well, let's go ahead and calculate. Well, if I were assuming that deformations are linear, then the net force that I get is stress times area. Well, what's the stress? It is the Young's modulus of the first material multiplying the corresponding strain. And then the second stress multiplies the second area, the second Young's modulus multiplying the corresponding strain. Strain is just like stretch, the same, because the two plates are parallel to each other. I extend both biological structures simultaneous. So that's equal to the force. And I know that this is 25 millimeters squared, this is MPa, this is 1, epsilon plus 19.63 millimeters squared, but multiplies 5 MPa. Epsilon is 80 newtons. So units are consistent. You can immediately go ahead and solve for the corresponding strain, which you will find to be 0.65. Well, yes, of course you're going to predict a large strain, but the point is whether that prediction is correct or not. And you see that now we have a huge error, 0.65 versus 0.75. So this is clearly not accurate. And that's why you need to use nonlinear elasticity. So if the deformations are going to turn out to be elastic but large, you have to use a model that is suitable, a nonlinear elasticity model, because otherwise you will not be able to make good predictions in these types of applications.